Will Fithian here at Berkeley will give one of the first of his 2 talks on statistical inference basics.
Hi, so yes, I'm Will Fithian, and I have 2 hours to tell you basically the content of my 1 semester course. So these are the topics I'm going to try to cover. If you've seen all of these before, I won't be offended if you get up and leave. Okay, so we'll just start out by going over the sort of most basic statistical problem that we might solve, estimation. Okay, so to begin with, what is a statistical model? It's just a family of candidate probability distributions for some data that we observe. So we'll say we use a notation, we could just say P. Script P is just a set, and we have a distribution P theta for each value, little theta, coming from a parameter space, capital theta. So this notation is, of course, suggestive that theta is a real number or a real vector. In fact, we could use the same notation if capital theta were some huge infinite dimensional space. So this doesn't just cover what we would usually call parametric inference, but we're going to certainly focus on those examples. So a few simple examples that we'll talk about. So X is binomial n theta, or here theta is in the set 0, 1, or could be X is normal theta 1, where now theta could be any real number. Or a sort of more non-parametric example, we could just say, let's say x1, this is getting closer to sort of realistic example we might deal with in real life. We have x1 up to xn, our IIDP. y1 up to ym, say, our IID Q, and maybe we have no idea what P and Q are, but we might want to do something like test whether they're the same thing, or compute an estimator or a confidence interval for the difference in means between these 2 distributions without having to worry about what parametric form they take. Okay, so in estimation, an estimation problem, we observe data that just one draw from one realization from one of these distributions, and then we have to, our goal is to sort of guess something about the distribution, and then we guess some estimand just any function of the data. So in these first 2 cases, g of theta is probably just theta, whereas here it could be something like the expectation of q minus the expectation of p. An estimator delta x is a function of the data that somebody intended to be a good guess of G. g of theta. So any function of the data is also called a statistic. Of course, it's important it can only be a function of the data, not the parameter, obviously, because we don't get to see the parameter. And so we want to guess as well as possible. So to start thinking about how we might come up with a good estimator, we have to start off by saying, well, what would make us happy? What aspect of a guess would actually make us happy? So the next thing we define is a loss function. Say L of theta d is just a function, so whatever the parameter was and whatever we happen to guess for g of theta, the loss function is like minus of the utility function. It tells us how unhappy we are with that outcome. Is how badly we do. Just say for guess, if we make the guess d, and the true parameter was theta. So the typical, or let's say the example you see probably more commonly than any other would be the squared error loss. So here, L of theta d, we could define it to be d, what we do guess, versus what we were trying to guess, quantity squared. Okay, so this is how well we do for a particular, say for any given realization, but we have to design an estimator. So when we design an estimator, we don't know yet what the data are going to be. We certainly don't know what the parameter is, but we want to come up with an estimator that's going to do well most of the time. It's going to give us a good loss most of the time. And so we define the risk function, or the risk is like the expected loss function, or also called the, like minus the expected utility function. So the risk now, the risk is a function not only of the parameter, but now of the estimator. It is how badly we do on average. So it's expectation theta of L theta delta of x. And so, so this we call the squared error loss. And if we were using the squared error loss, then the risk would be exactly the mean squared error.
So you needed a prior on theta now for the risk?
So that's a good question. No, so the risk is a function of theta. So we're not averaging over theta. Okay. Okay. In some corners of the mathematical world, people put the dummy variable, the thing you're integrating over, in the subscript here. We don't do that in statistics. In statistics, if you're always integrating over everything in the problem that's random. In frequentist statistics, theta is not considered random. It could be, in which case we would always integrate over it. But so here, when I say E sub theta, I mean the expectation doesn't have a meaning until I tell you what theta is. Expectation with respect to which measure? The measure corresponding to theta. And so that's what that means. Yeah. And if there were anything that we didn't want to average over, then I would have to say I'm conditioning on it. Yeah. Okay. Thank you. Okay, so this risk is a function not only of the estimator. So this is our choice. Our choice variable is what estimator we use, but what we don't have control over of what nature chooses is this parameter theta. So let's just do a really simple example. Three estimators for the binomial. So suppose that x is binomial n theta. And let's consider 3 possible estimators. So first, let's call delta 0x. This is the most obvious estimator you would think of. So I have n coin flips. Each one has a probability of coming up theta times. Let's just take the empirical fraction of times when x comes up heads. So that's an obvious estimator. But is it a good one? Is it the best one? This is in question. So let's consider another estimator, delta 1 of x. And we'll just say x plus 3 over n. And let's put in a third one, delta 2 of x. And that's x plus 3 over n plus 6. So for each of these, we can people see this? Plot. Oh, does the camera can only go so low, huh? No. Okay. Good. Thanks. So here, if I plot the mean squared error, or aka the risk function, against the parameter theta, okay, so we know that delta 0 of x, the expectation is just theta, so the mean squared error is exactly the variance of delta 0. And we know the variance is theta well, it's 1 over variance divided by n squared, so it's 1 over n times theta 1 minus theta. So we can just plot that to the parabola. And we always get it exactly right if theta is 0 or 1. So this is for delta 0. For delta 1, it actually looks like delta 0, but it happens to be shifted up. That's not so great. And then for delta 2, it's flatter than delta 1. So, okay, so a couple things just to point out about these functions. So delta 0 and delta 2 are definitely better than delta 1. So we say delta 1 is inadmissible in the sense that there exists another function, there exists another estimator that we could have chosen whose risk function dominates it. So dominates it means that the risk function is always at least as low. We can find another estimator with the risk function always at least as low and strictly lower at some point. So you would think from the name and from what the definition is, we would never ever use an inadmissible estimator. That's almost true, but it gets more interesting than that. We're not going to go into that, but it's not quite always true. But in this case, we have the right intuition that this is just a bad estimator. But if we're comparing delta 0 and delta 2, it's not really clear which one is the better estimator. Right, so they just, neither one is uniformly dominating the other. And in fact, so you might hope that we could find a fourth estimator that uniformly dominates all three on this board, and furthermore dominates every other estimator. But we can sort of see immediately that there's no hope of that. Because consider the estimator where no matter what happens, I always guess theta equals 0.5. I cannot possibly beat that estimator if theta really is 0.5. So there is no hope of finding one estimator that is, at least as good as every other estimator everywhere. So our only hope is to try to come up with a way to compare risk functions that don't uniformly dominate each other.
How do you draw these functions?
Badly, I guess. What do you mean?
I mean, what are the parameters? How do you find theta? What is the relation?
Oh, if I wanted to plot them on the computer, so I'm just plotting the mean squared error. Let me postpone that a couple boards down the road to when I talk about the Biasvariance tradeoff. but well, okay. So we know the first two moments of x,
Yeah.
and so we can compute the mean squared error. That would be a shorter, yeah, that would be a shorter. We know the first two moments of x as functions of theta, and so. Okay, so we're never gonna hope to find one estimator to rule them all. So how can we actually proceed here? It's not very satisfactory to just throw up our hands and say you might as well choose the one that always chooses theta to be 1/2. So there are a few different strategies to resolve this, and really you kind of have to bring sort of knowledge about the problem or your more sort of scientific motivations into the problem to really choose between these in any particular case. But some typical strategies to resolve this ambiguity. So first would be summarize the risk function as a scalar. And the two most common ways of doing that would be worst case risk. So, well, I'll do average case risk first. Average case risk and worst case risk. So in average case risk, we just take the average of the risk function, but now the question is average with respect to what way of averaging over the parameter space, average with respect to what measure, and that measure we call a prior distribution. So we have some measure lambda on the parameter space. Notice you don't have to bring in any kind of epistemological trappings about sort of having a subjective belief about the data. We can just say we're doing average case risk here. So we have some distribution on the parameter space capital theta. And then we would try to minimize over our choices of estimator. We find the estimator that minimizes now the integral over the parameter space. Averaging with respect to that distribution. So the simplest one to take there would be just the uniform distribution from 0 to 1. If we did that, I think we would get x plus 1 over n plus 2, and that would be the best estimator in that sense. So this is called the Bayes risk. This risk is called the Bayes risk for the prior lambda, and the actual estimator that minimizes here is the Bayes estimator. So I'll talk in a bit more depth about Bayes in a moment, but let's move on. So the second way to summarize would be worst case risk. Best case risk is not really in play because we would choose the one, we choose some deterministic estimator, but worst case risk is pretty reasonable. So then we can try to minimize over delta now the supremum over the whole parameter space of the risk function. So this is called the Minimax risk, and so here where we have sort of an intuition that nature is drawing the parameter from some distribution, and then we have to estimate it. Here instead we have a more game theoretic intuition where nature is going to wait and see what estimator we choose, and then choose the worst possible parameter to mess us up. I saw a question. Yes.
Why stop there? Is there something like the variance case risk where you want to be always kind of the same mistake no matter what happens?
The what case risk?
Like minimizing the variance of
The variance of the risk. Well, it's interesting you should ask. So it's not always, I don't know that this is a theorem, but in many problems, the Minimax estimator turns out to be a Bayes estimator. And it's a Bayes estimator for which you have some kind of Nash equilibrium with nature. So there's some Nash equilibrium choice for nature to choose the least favorable, we call it the least favorable prior. And with respect to that prior, we actually get a flat risk function. So if, in fact, you can prove that so it's actually a very short proof, if you can find a Bayes estimator with a flat risk function, then you know you have the minimax risk. Because the only way to have a better minimax risk for any estimator, you would have to dominate that risk function, and no Bayes estimator can be dominated. Okay, sorry. Actually, these are a few good theorems that you can sort of quickly see in your head. Any Bayes estimator is admissible. Why? If I had say I have a Bayes estimator. If you tell me that you've got another estimator with a better, whose risk is strictly dominating the Bayes estimator, well then the Bayes estimator can't actually have the best average case risk, right? And in particular, if I can find a Bayes estimator with a flat risk function, so because it's a Bayes estimator, it's admissible, and it has a flat risk function. And so there couldn't be, let's say I have a flat risk function here. I can't squeeze in any other risk function that has a smaller supremum, because then it would have to always be smaller than this risk function. So any Bayes estimator with a flat risk function actually is minimax. So maybe that's an partial answer. I'm sure that from time to time other people have come up with other ways of summarizing the risk function. I mean, I guess there are so-called adaptive minimax rules where so I guess there are more complicated variants of minimax. I'm not that aware of other ways that people have tried to do this. Yes?
Just to understand on this example, what would be the worst case risk estimator for the binomial?
The minimax risk estimator for the binomial. Okay, so I don't know off the top of my head, but and it would depend on n. Probably would depend on n, but it would be. We would look for a prior that makes the risk function flat. That's how we would find the minimax estimator. And so it would be, there are not that many priors to choose from in some sense, so we would, there are a lot.
But the intuition would be that the delta 2 here somehow would be better because the maximum of the function is lower than the delta.
Oh, right. So among these three, delta 2 has the best minimax risk.
Right.
Yeah, but there is one that has a better minimax risk, and it has a flat risk function. To find what that is, there's some math. You find the prior that makes. I don't think that there's sort of a way to turn the crank and do the computation and get the minimax risk, but
I mean, in this picture there's no prior, right?
In this, no, we're just plotting risk functions.
In this case, there's no prior.
That's right. The worst. Okay, so the worst case risk, there is no prior in setting up the problem. It so happens to be the case that most minimax estimators are also Bayes estimators.
So it's more like a heuristic that you would do to find. Like if you can find a prior such that
Sure.
it's one way, sort of.
Yes.
Okay.
This is related to the compactness of the underlying estimate.
Yes, it is. And in fact, in this problem, just taking x to be the estimator is minimax, but it's not a Bayes estimator. So minimax estimators don't always have to be Bayes. That's a good question. Okay. So, okay, so we can summarize the risk as a scalar, and then we get the average case risk or the worst case risk, Bayes and Minimax. And a third way that people have tried to break this ambiguity is by putting some kind of constraint on the set of estimators that we can choose. The most common one historically being to require that the estimator must be unbiased. So the second way would be to constrain the estimator. So there might be some natural property that you think the estimator should have. You might think it should respect some symmetry of the problem, or you might just say, no matter what theta is, I want to have an unbiased estimator. So an unbiased estimator, so for example, consider only unbiased delta. So unbiased means that the expectation is g of theta for every value of theta in the parameter space. And it turns out that if we, okay, I've erased them, but so there are a lot of problems where if we only make this requirement, then there actually is one estimator that is uniformly better than all other estimators. And depending on the problem, people sometimes find this to be a natural requirement. So I think that this requirement of unbiasedness, however, has somewhat fallen out of fashion in the last few decades. So now bias is viewed more as something to be managed than something to be that you would try to completely eliminate. And that brings me to my next topic, which is the Biasvariance tradeoff. So we can write the MSE of an estimator, the expectation delta of x minus g of theta squared. So here I'm going to define mu sub theta to be the expectation of delta of x. And okay, just to simplify the notation, I'm going to use theta here instead of g of theta. And so mu sub theta would just be equal to theta if delta of x were an unbiased estimator. And so this leads us to a very famous decomposition of the mean squared error, where we just add and subtract mu theta. And so what do we get? We get a sum of 3 terms. I'll start again here. Okay, so we get a sum of 3 terms. Delta of x minus mu theta squared. So that's the variance. Plus the expectation of mu theta minus theta squared. And here we don't need the expectation anymore because these are just real numbers, minus 2 times the expectation of something that has mean 0 times something that's not random. And so this whole thing goes away. And so what we get is the variance of delta of x plus, and this is the bias squared. The bias theta of delta of x plus the bias squared. And so this is completely precise if we're taking the mean squared error to be our risk function. More generally, we may be interested in many other risk functions other than the mean squared error. We sort of still use this Biasvariance tradeoff as sort of a metaphor that you have some estimators that really intensely regularize the answer. So this one here, this is equivalent to saying, pretend I'm going to make up data where I flipped the coin 6 times and I got 3 heads. And essentially it results in a convex combination between this estimator and 1/2. So this estimator, it has lower variance because it's a convex combination between something that's random and something that's fixed, whereas here it's just the random thing. So this one has lower variance, but it has some bias. And in the places where delta 2 is losing, it's because the bias wins out. In the places where it's winning, it's because the variance wins out. And so more generally, we sort of think that for all kinds of, in all kinds of statistical problems that we approach, we very much think in terms of Biasvariance tradeoff.
Is it clear that it has to be a trade-off and you cannot simultaneously use both?
Well, it depends on what you start from. If you start from a bad enough estimator, you certainly could. But if you have an admissible estimator, then you couldn't uniformly improve both.
Corresponds to the same.
Okay. So next I'm going to talk a little bit more about Bayes risk. So here we've sort of introduced Bayes risk, the Bayes risk and Bayesian Bayes estimators from a completely frequentist motivation. But more generally, in Bayesian inference, we might actually sort of start off and interpret this capital lambda as an actual sort of prior belief over what the value of theta might be. And in that case, there's actually a lot less that we need to say. So all the things that we've been saying here about trade-offs and properties of different estimators, they become sort of moot. So in Bayesian inference, everything is in some sense a lot more simple. So if we actually sort of believe capital lambda as a real prior distribution, then things simplify considerably. So say, we have some prior density, lambda of theta. And p theta of x is the density of the distribution in our model corresponding to theta. So now we're sort of thinking of the parameter and the data as being random. So now if it's really true that theta is coming randomly from lambda and x given theta is being drawn from p theta conditionally, then we actually can say exactly what then theta given x. You can just write down what the distribution is. Let's write p of theta given x, and it's just proportional to the prior times the likelihood. So this is the posterior distribution, well, posterior density in this case. And it's a complete, so it sort of describes if this was our belief about the data before, about the parameter before seeing the data, and then we see this data, then this posterior density describes our belief state about what the parameter should be after seeing the data. And it's and we don't really need to talk that much about estimators or hypothesis testing or confidence intervals, because the posterior is just a complete description of everything that we might believe about the data. So you might want to summarize it in some way for some reason. And the posterior, it sort of combines the prior. So let's say we have the prior and the likelihood. This is lambda p theta of x. And then they sort of get combined into something that hopefully looks a lot more narrow. So now we have a lot more information about the distribution. And so, for example, if we do for whatever reason care about coming up with an estimator that has the smallest mean squared error, then it's very clear how to do it. We just take the posterior mean. So the Bayes estimator for the mean squared error is just the posterior mean. So to minimize, so we want to minimize E. Now lambda is the distribution controlling everything. Well, we first can condition on x. So we can just condition on x. And so now, once we're looking at this internal conditional expectation, well, now after we've conditioned on x, x is just fixed. Yeah, x is just fixed. And so we're going to draw some g of theta from the known posterior distribution of theta given x. And we want to choose a number, delta of x, that's going to be as close as possible to it in squared distance. And it's not hard to show that the way that you minimize this function is to choose. So this number we get to choose after seeing x. We choose this number to be the mean of the distribution of this number. It's not hard to show. And so very similar arguments give Bayes estimators for really any other loss that you would want. You wait and see the data. Now once you've seen the data, now the theta is going to come from some distribution, and so you can just compute exactly what the conditional loss, the conditional expectation of the loss is going to be for any choice of your estimator, and you pick the one with the smallest.
Sorry, you meant sub lambda in both cases there?
Yeah, they both depend on lambda. Yeah.
And it is the posterior lambda over on the right there, or is it?
No, this is the measure lambda from which theta is marginally drawn.
Okay, and on the right there, you say posterior lambda. Did you mean in the graph?
Posterior. Oh, sorry. No, I didn't mean that to be labeling lambda. Thanks. Yeah. Right. So okay. So again, the only reason I'm putting this in subscript is because what this expectation is depends on what the prior is. So now the prior is the thing that's fixed that drives what we integrate, what measure we integrate with respect to. Okay. So the only question that so Bayesian inference, it sounds great, and generally there are very strong reasons to want to do it. So the question is, why don't we always do it that way? So first of all, computationally, as I'm sure many of you know, computationally we can sort of run into more problems than might look evident. In particular, this sort of proportional symbol is doing a lot of work here, and the devil can kind of be in the computational details for a lot of Bayes methods. But I would say there are bigger issues, and in sort of a lot of statistical and a lot of scientific applications, the real question that we might snag ourselves on is just where are we going to get the prior. So there's the question of sort of where is the prior going to come from. So there are a few different possible answers to this question. So first, it could sort of come from direct prior experience. So maybe we actually have a lot of parallel instances of a similar problem to solve. In that case, we could just sort of estimate the prior from all of the other instances. This is usually called empirical Bayes. This is essentially uncontroversial. Another possibility, however, would be that you somehow, that really the prior just sort of reflects your subjective beliefs. So you just search inside of yourself and you ask yourself, what is the prior? You don't need to get it from anywhere. It just comes from inside of you. It just reflects your own opinion. So in a scientific paper, if you publish the posterior, then part of what you're publishing, I suppose, is what your opinion is after seeing the data. And so people sort of find this to be less objective, so they find some problem with that. And I would say, so maybe some people would have a philosophical problem with that, but even if you don't have a philosophical problem with that, it becomes very difficult to express what your subjective opinion is over an extremely high dimensional parameter. So here we've been talking about the binomial or the normal distribution, but I also mentioned, remember, we could have a problem like x1 up to xn are IIDP, y1 up to ym are IIDQ. So this would be a typical example in statistics where there actually is a lot that we can do with this problem, just leaving p and q as being completely unknown. From a frequentist perspective, from a Bayesian perspective, before we even get going, we have to somehow specify what our joint distribution is over these let's say two distributions over the real numbers. This is a very hard thing to express. What is your opinion that p has a little wiggle here? Also, whether q has a little wiggle over here, and moreover, what's the joint probability of those two things together? It's not really plausible that you could even elicit what your opinion is, let alone have a reasonable opinion. Okay, so that's enough rambling about priors. So any questions on this? I'm about to move on to hypothesis testing from estimation. Yes?
Why do you insist that G is a function and not a distribution?
G of theta?
Yes. Why can't you sort of output a random guess with your own coin toss? Why is it so important to have a specific number?
Do you mean why isn't delta of x random given the data?
Sorry.
Oh, okay. So why couldn't we choose a randomized estimator? We could. So there might be some contexts where you would consider that. For a lot of risk functions, so generally for a convex risk function, you would make your loss worse. You would make your risk worse by randomizing. So, so for most risk functions that we would consider, that we usually consider, it wouldn't really help. But more generally, it might help, I suppose.
Other than there could be computational benefits in that the optimal G of theta might be hard to guess, but from a space, a typical one might be required.
The delta of x, you mean, or
G of theta, is that right?
Yeah, I was confused. The delta of x is our guess. We see x, and then we want to guess.
yes?
So I guess maybe you will do this later, but maximum likelihood estimator versus mean squared error.
Okay. So these are all very sort of finite sample ways of looking at the world. The maximum likelihood estimator is a great all-purpose estimator that I'll get to later. We won't have time to talk about sort of the optimality properties of the maximum likelihood estimator, but the maximum likelihood estimator in nice asymptotic regimes basically does as well as you could hope for asymptotically, and it's very easy to just say what you're doing. So there can be a lot less ambiguity in the nicest asymptotic regimes. But we spend less time studying the nicest asymptotic regimes. Yes?
What does MSE mean on this board?
Mean squared error.
So
If the
mean
mean
squared error is posterior mean?
the Bayes so if our risk function is the mean squared error, then we can't uniformly minimize mean squared error. So we said a strategy is we're going to take the Bayes track. So we're going to use a particular prior.
Oh, so lambda is the prior distribution. That's what you're integrating against for this Bayes estimator.
Yeah, maybe I should have said the Bayes estimator for the squared error loss.
You end up with posterior mean when you do that. That's
yes,
okay,
yes.
got it. Thank you.
If we carried out that program for the prior lambda here. Thanks. Yes.
So in that line, so we are not taking the expectation of the ctax minus g theta.
In this line?
Or above.
Or this? Oh yeah. So to make it easier on me, because g of theta often is theta, and so so I didn't have to write g as many times. I just dropped the g in this derivation. Yes.
Is there a framework to look at? Suppose you take a different prior from, let's say your random variables are coming from a certain prior theta naught, and you take some theta dash. Some robustness sort of framework where you won't do as bad.
So I'm sure there is. That would be not within my area of research expertise, but I'm sure people. So some people do. So here we're sort of mixing philosophies, not necessarily in a bad way, but from the Bayesian philosophy, if you sort of have not really. Okay, so you're talking about from a frequentist perspective. What are the frequentist properties of a Bayes estimator when the prior is misspecified? And I know that people have studied this, but I don't know that much about where to direct you. Yes?
You said something about if you don't have a prior, you can do some empirical based thing where you sort of find distribution from samples.
Yes.
So how do you formalize that? Because isn't this whole estimation problem to find what the distribution is?
So the way we would formalize it is usually we would have some kind of, generally for empirical Bayes, you have some kind of repeated structure in the problem. So for non-empirical, just regular hierarchical Bayes, you can do this too. So you can say, so let's say I have some, so the xi given theta I, so the I of baseball players batting average, empirical batting average, conditional on its true batting average, let's say is binomial ni theta I. But the baseball players, the IF baseball players' true batting average is also coming from some distribution, let's say, not normal, let's say beta, alpha beta, but so this would be sort of a regular Bayes setup where the problems would just separate out if we specified what alpha and beta are. But now that we actually have many baseball players, we have an opportunity to learn alpha and beta. So we could do this in a completely Bayesian, not empirical Bayesian framework, but just a hierarchical Bayesian framework. To say then also we'll say alpha and beta come from some distribution lambda. So maybe we give. So now I have to specify lambda. Yeah. But actually, so once I set up this problem, specifying lambda, there's sort of less at stake. It's hard to formalize what that means, but practically speaking, there's less at stake in defining this, as long as because we have we sort of have a lot of repeat observations potentially letting us nail down alpha and beta. So if you have really good data on a parameter, it doesn't matter that much what prior you put on it. This is sort of a folk theorem or something, right? There are real theorem versions of that statement. But if you have a lot of data about something, then it doesn't matter that much what prior you put on it. So here, we might be able to learn alpha and beta very well, and so we could just put a very sort of wide prior on theta, sort of agnostic prior. And we probably would get pretty good estimators for pretty good inference on alpha and beta. Or at this point, though, if you said there's so little stake on the prior, why put a prior on it at all? Why not just take these to be numbers that we should, unknown parameters that we can estimate, that we don't have to worry about choosing a prior at all. And there's not that much difference practically between those two alternatives. So I only have 5 minutes, which is not enough time to start with hypothesis testing. But this reminds me, I should have mentioned another way to come up with priors. Is a lot of times what people will do is they'll just choose a very wide prior. So they try to put a very wide prior. Say if theta is some real number, you could put some prior that spreads information way across a huge range of values, way more than you think is actually plausible for the parameter. And the idea behind doing this is then at that point, the prior has less influence. You're sort of not you're not injecting your opinion into the problem. But then you lose a lot of the really nice interpretations of all the things I said about Bayes, is that all you need to know is the posterior. Well, if you chose the prior if you chose the prior based on some automatic rule rather than what you actually believed, if the prior isn't what you believed before seeing the data, then the posterior isn't what you believe after seeing the data. So it's so things conceptually simplify less, and we probably have to at that point think of it more as a frequentist estimator. But it may be a very good frequentist estimator, and so we shouldn't reject it. Yes?
So following up on an earlier question, and kind of related to that, so the max risk doesn't depend on on a prior.
That's right.
The Bayes estimator depends on the prior. If you took the integral of the fifth power of the risk, then that would depend on the prior, but it would look more like the max risk.
Oh.
So.
Yeah, that's interesting. Yeah.
Interesting.
Just a thought.
Okay, well, I guess at this point, there's no need for me to insist on speaking for 3 more minutes. So I'll see you all after the break.